Morning. Well, we're here again because I didn't have a chance to finish this up yesterday. Had to get going to get lab set up. So this is going to be a pretty short video, but just dealing with the last part of the packet here that we didn't get to yesterday. So yesterday we looked at all kinds of different structures, and we also talked a little bit about electronegativity and polarity. So the last part of the packet kind of deals with this and talks about what we can do when or how we can figure out if an entire molecule is polar, not just the bonds inside of it. And it kind of speaks to this question number 15 here. True or false? A molecule that has polar bonds will always be polar. If true, explain why. False, provide a counter example. So this is false. And let's take a look at why. Get another piece of paper here. So we talked yesterday about how an individual bond, like let's say a CO bond, can be polar or is polar because the oxygen has the higher electronegativity and the carbon has a lower electronegativity. And that means that the electrons in the bond here are pulled toward the oxygen. So that means this side of the bond is going to have some negative character, and this side of the bond is going to have some positive character because of that lopsidedness. The negatively charged electrons are pulled over to one side, so it's more negative on that side, less negative or positive on the other side. All right, so that's the basics of how a bond can be polar. But when we put these types of polar bonds into a molecule, then we have to look at the separation of charge in the entire molecule. So let's look at CO2. Here's the Lewis structure for CO2. And we want to know, is this entire molecule polar or nonpolar? So to do that, we first need to examine the individual bonds. So we first look at the individual bonds in the molecule, of which there are two CO bonds, right? One here, one here. So let's look at the one on the right first. So we just look at this bond, and it doesn't matter if it's double, single, triple, whatever, but just that bond, we know from what we just talked about that the electrons are pulled toward the oxygen, which means we're going to have some negative charge on this side and some positive on this side. And then we do the same thing for the other one. We say, okay, well, this is also a CO bond. And in this case, the electrons are pulled this way. And so there's some negative over here and some positive over here. And now if we put that all together and we look at the whole molecule, what we see is there's kind of negative on the outside and positive on the inside. But if you imagine what that looks like from kind of the outside, remember that molecules are kind of like big spheres mashed into each other like that or something. So the idea that there's some positive in the middle and then negatives around the outside really means that there's just negatives around the outside is what that would look like to other molecules. So this molecule overall is nonpolar because there isn't one polar or one positive side and one negative side. The positives and negatives are symmetrically distributed around the molecule. So overall, carbon dioxide is nonpolar, even though the bonds inside of it are polar. So this happens anytime we have a highly symmetric molecule with, even if it's made of polar bonds. So for example, here's a couple more examples. CF4 is tetrahedral. Here's our Lewis structure showing the geometry. And this one can be kind of hard to see, but the CF bonds are indeed polar. And because the tetrahedral is perfectly symmetrical, or the tetrahedron is perfectly symmetrical, these all end up canceling each other out. And so you have like electrons pulled this way, this way, this way, this way. That all cancels itself out, and so the overall molecule is again nonpolar. Now let's compare that to NF3, which is similar but has a trigonal pyramidal structure. Like this. And so now we actually do have an overall polar molecule. What we can say here, what we can see is there's a difference in electronegativity between nitrogen and fluorine. Fluorine's the most electronegative element, so the electrons are pulled toward the fluorines in each case. So we have, some negative, positive, negative, positive. The reason I'm using multiples here is because I just want to show that it's like some negativeness rather than an individual charge like an ion. When we put just like a positive or a negative charge, we're kind of saying this has a charge, it's an ion. That's not really what's happening here. It's just that the electrons are more to one side than the other. So if we look at this whole molecule, we can see the negatives pulled out to the fluorines and the nitrogen positive. So if we imagine kind of like cutting this molecule in half in this plane here, like underneath the nitrogen, it would be mostly positive on top and it would be mostly negative on the bottom underneath that plane. So the fluorines would be underneath and the nitrogen would be on top. And because you can make that cut and say there's a positive side and there's a negative side, that tells us that this is an overall polar molecule. If it were flat, like for example, BF3, which is trigonal planar, doesn't have that tetrahedral angle. It has just the planar angle. It's all flat. It's all in the same plane as the screen here. Well, then we don't have anywhere we can cut it and separate positive and negative, because the boron in the middle is more positive. The fluorines are on the outside are more negative. They cancel each other out, and there's no like positive negative cut. So this one's also nonpolar. And only this middle one ends up being polar. All right. So then moving back to some of these. So when we look at a molecule like this, like in this table, we need to be able to do a couple things first. So first, we need the Lewis structure. So all the stuff we did back on Monday, that comes first because we need the right Lewis structure for the molecule. Then when we have the Lewis structure, we can look at the bonds and decide if they're polar or not. And then we can try kind of adding those up in the whole molecule and see if the whole molecule is polar or not. So we've done some of these in the examples. Go back up and you can look at those. Let's try one more to finish this up today. So we'll look at OF2. All right, so we'll start from the beginning. We're going to get the Lewis structure. So we count up the electrons, 6, 7, and 7. Is 20. Then we draw a structure. Then we add in our non-bonding electrons. And if we run out of electrons, then we have to start thinking about multiple bonds. But in this case, we don't run out of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we're good. Okay, now we have a Lewis structure. And we can answer the first question, does this contain polar bonds? And it does, because there's a difference in electronegativity between oxygen and fluorine, about 0.5, I believe, maybe more. I think it's about 0.5. So those are polar bonds. So OF2, where is it? There it is. Does it contain polar bonds? Yes. The OF bonds individually are polar. Is the molecule polar or nonpolar? Now, here's where we need one more step. We can't just say, well, okay, it's negative and positive in the middle, so that's symmetric, so they cancel each other out, so it's nonpolar. And that doesn't work here because we don't know the shape yet. We drew this thing straight like this, linear, but we don't actually know that it's linear yet because we haven't thought about that. We have to use those skills we did yesterday to figure that out. So what is the shape of this molecule? Well, let's go back to that table. We have to look at the number of electron groups or domains, and then how many lone pairs are on that central atom. So we've got central atom's oxygen. We've got 4 electron groups, 1, 2, 3, 4, or domains, and then 2 lone pairs. So 4 electron groups, 2 lone pairs gives us a bent geometry, just like water. Right? So that means that the actual shape of this molecule should be like this. Because those 2 lone pairs on the oxygen take up those extra spaces in the tetrahedral geometry. So now that we have this kind of a shape, we can reevaluate our polarity, and we can say, all right, well, if we've got electrons being pulled toward the fluorines and away from the oxygen, then we have a really nice separation here, right? We can draw a line straight through the molecule, and we've got a positive side on top and a negative side underneath. And so that very much is polar. If you have that separation where one side of the molecule is positive and the other side is negative, we can call that a polar molecule. So that is polar. That's why the shape is so important. If we stuck with a linear shape, we would say that overall this is nonpolar. The 2 sides cancel each other out. But as soon as it bends, now we have the negative side and the positive side, and that becomes polar. All right, so that is how that works. Let me know if you have questions. Give these other ones a try. Hope the homework and all that goes well also. And yeah, I'll see you on Monday evening.